Okay, hello everyone, welcome. Let's get going. Today we're talking about perfect hashing. Okay, so all of you at this point in your computer science careers know about hash tables. And so you know that the goal of any hash table is to map keys to a bunch of buckets in a hash table. The hash table is going to resolve collisions for you. Collisions are kind of inevitable. And that ultimately, by expectation, the hash table is going to guarantee constant time access cost for in expectation for a random key. And hash tables are used all over the place in database systems. That's probably needless to say, but just to name a few places where they are used. So they're used to implement hash join algorithms. They're used just to implement in-memory indexes, and also very widely for key value stores. Okay, so as I said, any hash table has to implement some sort of collision resolution strategy. And here are some types of strategies that you probably have seen before. You've probably seen chaining, right? Just forming a linked list with buckets that overflow. Probably seen open addressing. The most famous of these is linear probing, where you're just kind of pushing elements to the right to clear space. You might have also seen cuckoo hashing, where every element can map to one of two buckets. Then if an element goes to a bucket that already has an entry, it kicks the other entry to that entry's alternative bucket. This can continue recursively. Anyways, all of these collision resolution strategies rely on having access to the actual keys, right? Because they move keys around different positions, and so when you're doing a query, well, you have to check a bunch of positions, but because you don't exactly know where the collision resolution strategy has placed each key, you have to have the keys themselves to actually find, to actually know that you've reached the element that you're trying to find. Okay, but here are some issues with storing the actual keys in a hash table. So first of all, they take up space. And second of all, suppose that the keys are variable length. Storing variable length keys inside a hash table is not a trivial thing. It's probably going to require you to have some sort of layer of indirection, which is going to mess up your performance, because you might have to store a pointer to a key instead of the key itself inside the hash table. Okay, so we want to avoid these issues because we really care about space and performance in this course. And so we introduce perfect hashing. And the core idea here is, let's have a hash table that doesn't store the actual keys, but it still implements collision resolution to be able to map a given key uniquely to a particular payload that corresponds to that key, right? So there is a map. The map is collision-free, but we're not storing the actual keys. But giving a key that we did actually insert, we can guarantee to you that we're going to return to you the correct payload. That's all that it is. It's going to involve a higher construction and insertion overhead than regular hash tables to resolve these collisions as they occur, right? But that's the trade-off. That's the trade-off, and that's going to allow us to not have to store the keys. Okay, makes sense? So far, it's pretty conceptual. And these are only actually useful, I should say as a caveat, they're only useful when you have queries to keys that actually exist. Why? What would happen, given what I've just described, what would happen if I issue a query to a key that I haven't inserted?
I'm not sure which hash can store.
Exactly. So it might actually map me to a payload corresponding to some other key, and I'm going to have no idea and no ability to differentiate. Yes?
So just to clarify, the reason you have no way to differentiate is because you haven't inserted like the non-existent key.
Yes.
So you haven't resolved the collision.
Exactly. Exactly. Okay. Makes sense to everybody? Good. So provided the keys that I actually inserted, I guarantee no collisions, but I can't guarantee that for keys that I haven't inserted. All right. So here's just an example application in key value stores. Right? So in key value stores, you'll typically have a situation where you have a bunch of data on, say, an SSD, and you'll have an index in memory, right? And so inside storage, you're going to have key value pairs. And here I'm illustrating them. Then in in memory, you might map these key value pairs using key value pointer, key pointer pairs. Right now, there are key value stores that actually store the full keys in memory. So Bitcask is an example of such a system, right? But as we said, in such systems, we care about the memory footprint for this index. So, we typically don't actually want to store the actual keys inside of this index, right? Because memory is expensive. Okay, now even without perfect hashing, we've actually already seen a solution to this problem of how to have an index without storing the full keys. Right? We've seen something that could be used for this purpose in this course. Can anybody point out what that is? Yes? Yes, that's basically right. So I'm just saying use a filter, right? But that could be something like a quotient filter, and that's going to store a fingerprint for each key instead of the key itself. Okay, so that's a viable solution. It's not a perfect hash table because you can still have fingerprint collisions, right, between different entries. Yes, so we replace the keys to save space. Okay, and now, with respect to this design, we can analyze, okay, what is the cost if we're issuing a query to a non-existing key or to an existing key with respect to the fingerprint length? Somebody have a suggestion? So suppose I'm issuing to this system with F bits fingerprints. I'm issuing a query to a key that doesn't exist. What's the expected IO cost? Yeah. F bits, do you say? So what I'm looking at is the number of storage accesses that I need to do to return the page containing that key. And so I think we're talking about different units somehow. Yeah? Huh? Okay, one assuming this is a key that doesn't exist. So you're correct in that it's one assuming that I had a false positive, but without assuming that it's a false positive, what is it? Correct. So it's 2 to the power of minus f. That's the probability that I get a false positive. And that also happens to be equal to the probability that I do to the expected IO cost. Okay? Cool. What's going to be the cost if I'm issuing a query to a key that exists? Yeah. 1? A little bit more than 1? 1 plus this, correct. Why? Yep. So in a given bucket that I go to and I find the given entry that I'm looking for, on average, there's going to be maybe one more entry. And this is the probability that I'm going to falsely match that entry and have to do 2 IOs. All right. So roughly these are approximations of what the cost would actually be. Okay, good. Now, let's suppose for a second that we only care about queries that actually target existing keys. And why? Perhaps because they're more common, or because we're interested in minimizing latency for queries that actually do useful work. Okay, so we don't care. So we only care about this metric. Right? And we observe, right, this one IO, we have to do one IO to fetch the entry from storage. We can't really do much about that. But we might ask, what can we do about this cost here? Because this cost, every now and then you have to do an extra IO. It messes up your latency. And this happens due to fingerprint collisions. Okay, so one thing that you can do is you can reduce this by increasing the fingerprint size. But that's just going to cost you my memory. So is there a better way? Okay, everybody with me? Okay, so the better way is perfect hashing, right? Because perfect hashing will guarantee to you that there are going to be no collisions. And okay, now we're going to start to look into this more closely. But so throughout this lecture, we'll cover 2 kind of variants of perfect hashing. One of them is called minimal perfect hashing. It's more space efficient, but it's actually only applicable for static data. And then we're also going to cover dynamic perfect hashing. That takes a little bit more space, but it actually supports updates and insertions. Right? You can modify the mapping and resolve collisions as you insert new entries. And we'll start with minimal perfect hashing. Okay, so just to kind of crystallize the problem here. We have an array with n slots, and we have n keys. And what we're trying to do is, okay, note that this array has a 100% load factor, right? So what that means is, right, in a typical hash table, we have some extra capacity to not lose too much performance as the collision resolution strategy is doing its thing. Here, we don't have any extra space. And what we're trying to do is establish a bijection between the keys and the slots. What's a bijection? It's a one-to-one mapping where, literally every key maps to one slot and every slot is mapped to by one key. Okay, that's our goal. And we want, okay, a bijection by definition is collision free. All right, so we might ask, suppose that we actually just take a random hash function. What is the probability that we'll actually get a bijection? A one-to-one mapping. Does anybody have a, well, I might as well show you this. So we're going to do that by looking at these two things. Does anybody have a sense of how and yes?
I would really answer the first question, which is like the impossible bisections. But in the general idea, what I'm guessing is, like, for example, the first key A can go to any one of the n slots, right? And the second one, the n minus one possibilities, and you kind of just
Correct.
But you don't have a probability, so it's changing over number of choices you make.
Yes.
Just like, when I make 1 over n and 1 over n minus 1 and for the part.
So what you're saying is exactly correct, right? So basically, after you assign each entry, right, you're restricted with respect to where you can assign the other entries. That's definitely going to play into our calculation of this probability. Yes. Why?
N factorial, n have them minus 1, like that minus 6 on. And then the denominator is you have n choices for A, n choices for B, n choices for C.
Yeah, excellent. So basically that's exactly right. So we compute this probability by looking at the total possible number of, like, bijections, which is equivalent to the number of permutations that you can have with n entries, which is n factorial. Right, and you also consider then the total number of possible ways of assigning n entries to n buckets, assuming that each entry can go anywhere and we don't care about collisions. Right, and we take that as a probability, and then you might ask, what happens as this expression increases? Can somebody tell me? It goes to 0. Correct. So to actually just answer this rigorously, first of all, you can use Stirling's approximation and simplify, right? And then you can take this n to infinity and just observe that it goes down to 0. So this seems pretty hopeless. So that's too bad. What can we do instead? Okay, so what we're going to do instead is essentially, okay, so this is going to be our minimal perfect hash function. And we're going to construct it. So we're not just going to choose it randomly and hope for the best. We're actually going to construct it with respect to the data. And we're going to use a small amount of metadata to represent this function. And that's how we solve the problem. We solve the problem using space. Okay, and this minimal perfect hash function, I mean, it's called a function. And this was confusing to me for a while, but just think about it. It's just a data structure. It's just a data structure that helps you map the keys to unique slots. Okay, and we're going to see a particular variant of minimal perfect hashing in this presentation called fingerprinting. As it's just a data structure, we can analyze this data structure with respect to the amount of memory it takes up, the query cost, and construction time. So this is exactly what we're going to do. And I should say, fingerprinting is it's a technique that I guess has been used for a while. It has emerged in various different contexts. There are various different papers with different variants that you can look at. I asked you to read one of them for the simple fact that I find this paper to be particularly accessible. It's also nice that they have a focus on experiments here. So it's a little bit more concrete. So this is the paper that I asked you to read. Okay, and here's how this algorithm works. We're going to start off with a bunch of keys, 6 keys in this example. And we're going to say, let's pick some random hash function and map these 6 keys into one bit vector with 6 bits. So the number of bits in the bit vector is the same as the number of elements that we're trying to map. Okay. So we're going to apply this hash function and we're going to get some random assignments. And there are going to be collisions in this assignment because we're using just a hash function, right? So there will be collisions. What we are now going to do, did anybody read the paper and knows what we're going to do? Okay, good. So, yes? You'll record which positions have collisions and which don't? Something like that. That's kind of correct. So in fact, what we're going to do is only take positions that one entry mapped to and set those to ones. This is kind of similar to actually what we saw in the last lecture with that like block index at the end of, right? If you remember in RocksDB, it's a little bit similar to what we're doing here. Anyways, but here we just have a bit vector. Okay, so we did that. This means that we resolved 2 entries. We have succeeded in kind of uniquely mapping 2 entries. Let's now continue doing this process recursively for the other entries that we did not successfully manage to map to a unique bit. Okay, so we'll now try to map these using a different hash function to a different bitmap that's smaller. And this bitmap only has 4 bits because now we're only trying to map 4 elements. Okay, we'll do this again. We succeeded with 2 elements. We'll set the corresponding bits to ones. That's good. But now we have to continue recursively, right? So we'll continue using a third hash function, using a smaller bitmap. And now let's say, maybe we actually succeeded. Okay, so now we have 3 bitmaps. We've managed to map every entry to a unique bit. What should we do now? This is already almost a complete data structure in some sense. But how you use it? Yeah?
Yes. Check if it's a 1. If it's a 0, then check the next bit.
So that's correct. And then how do you take that and actually kind of map that to a unique slot in an array? Okay, so let's see how to do that. So first of all, what we're going to say, this is just not even conceptual. This is actually how the algorithm works. We're going to concatenate the bitmaps. Okay? All right. And now we're going to say, we're going to define the bijection to be as follows. Right? So this is the array that stores like some payload for each key. And we'll say that in this kind of order of the ones, each one of them kind of maps to, right? The first one corresponds to the first slot, the second one corresponds to the second slot, and so on. Right? So this is the value corresponding to F, this is the value corresponding to C. This is our mapping. Okay? So now, how do we query this thing? The first part of what you said, Tony, is correct. Suppose we want to query for key B. We're going to start with the first bitmap. We know how long each one of the original bitmaps are, right? So we'll start by hashing B, and we find a 0 because we did not succeed for B in the first iteration of the construction algorithm. Then we will use the second hash function and try that on the second bitmap. And again, we'll find a 0 because, right, B only succeeded in the third iteration. Finally, we eventually succeed. And what do we do now? Yes. And the number of ones before will tell us what? Correct. And what is the basic construct for counting the number of ones that we've seen all over this course? Rank. We're going to apply a rank operation on this bitmap. So, Okay, so yeah, so we know that we found the entry, the first one that we found for B appeared at offset 10, global offset 10 of this bitmap. And we are going to take rank of 10 to count the number of ones before. And rank of 10 is going to return 4, and 4 is indeed the offset of this element B in the array of payloads. Okay. Yes?
I was still good worried about the conversion of process of maps until everything. Because as you can see, you already have 3 hash functions for like 6 elements.
So you're concerned about the number of hash functions we have to use?
Look like the number of bitmaps you know, how many iterations are you even?
Okay. So your concern is for what? For construction costs, query costs?
Yeah, I guess so. I guess that would be like how big is it like asset over like how big it can get.
Well, what's your sense? So how many bitmaps do we need?
I would say a good hash function on average allocates 50% of your keys to unique stuff. That's what I would guess. So something like that. So the maximum power of the event.
Okay, so the max, okay. So let's get to that in a moment. We're gonna do analysis of this thing in a moment.
You could also store prefix subsets. So you don't have to like do the full RAM. You can like store, because even if you combine them, you can kind of, you don't have to do all that work all the time.
Well, yes, you're preempting me. So how do we run rank quickly? And we do rank exactly as you said, right? We're gonna do exactly like a prefix sum array, all right? Which is like, basically the basic data structure that we've seen to speed up rank. We saw how to do that, I think, two weeks ago in the context of succinct sets, right? So basically you store the rank for like regular offsets and you store that in a separate array. All right, so this might go into a separate array. And like now, suppose we want to actually query for the number of ones before offset 10, right? So rank 10 was the operation we wanted to speed up. We'll just do, kind of 10 divided by 4. 4 is like kind of the interval between the different ranks we're doing. Just bringing us here. This 3, right, tells us that, by the time that we reach here, there are 3 ones that appear here in this array. Then we can just kind of scan the rest. And the last part of this, assuming that it's one CPU word, we can actually do using the pop count thing that we saw when we studied the rank and select quotient filter. All right, so this whole thing can actually be done in constant time. This mapping is going to add a little bit of extra space, but not that much extra space. So, it might add something like 0.1 something bits. All righty, so we can do all this fast, which is nice. Does this alleviate some of your concern?
Yeah, a little bit.
Okay, good.
I'm still very but it's very interested on the convergence aspect.
Right. Is that a question?
Building off this, it kind of feels like
Log n hash functions. As we will see, that's exactly correct. So there is a nuance here, and we'll don't say it yet. Okay, so first yes.
Why dividing by 4?
I'm dividing by 4 because 4 was the distance between my different rank samples.
Okay. So, okay. I thought the rank would be the end of each bitmap, but it's just evenly divided.
Oh, it's evenly divided, and you can think about it as an auxiliary array that's outside of the data structure.
And so you have to store this value in each bitmap, well, right?
Yes, you do. You do. That's going to be a little bit of extra metadata, but not that much. But you're totally right. Okay, other questions? Okay, so now we know the data structure. Now we can analyze it. So we might ask, what's the total bitmap size? Does anybody have a sense of how we might even begin analyzing this? So you reckon it might be something like n log n in terms of size?
think it's like N.
Uh-huh.
N. Outside.
2n. Okay, it's actually going to be close to that, but not exactly. Where did 2n come from?
It's everything's fine. Very different. The way you build in the top, that wasn't.
Okay, so you are correct, except for the part where you said half, because it's not exactly a half of the entries that succeed in each iteration. And we're going to look at that now. But first of all, let's see, but otherwise your intuitions are correct. Some other comments about how we might begin this analysis? Okay. So first of all, just like observe that in each iteration of the construction algorithm, we're trying to map a bunch of entries. So we have a few attempts, and then there's a bunch of entries that actually succeed, and the rest fail. Okay? Now we might ask, what is the total number of bits in this bitmap with respect to the number of trials that we've made? Right? Each trial is trying to apply one hash function on one key, mapping it to a particular bit. We might succeed and we might fail. At the end of the day, we've done X trials. What is the number of bits in the bitmap with respect to the X trials that we've done? Yeah. Each failure has what? Basically, that's right. Yeah. Yeah. So note that the total number of trials that you do is equivalent to the number of bits in this bitmap. Does that make sense? Right? For a given entry where I succeeded the first time, it only requires one bit. If it's an entry that I, attempted, 3 trials and I succeeded the third time, that entry will require 3 bits across 3 bitmaps. Right? So it's actually pretty. So this is the thing that we need to analyze, and this will tell us what the number of bits is in the bitmap. Okay. So now we might ask so now the question is really how many trials do we have to perform per entry before we succeed? Okay, and a bunch of you have kind of indicated that like the probability of success is 0. It's not actually going to be exactly 0. It's going to be a little bit different. So, okay, so let's ask this question. What is the probability that we succeed for a given entry in a particular iteration? And it's not half. But actually, by now at this course, you should have a sense of how to analyze this. Yes. Yes. Why? Yes. Yes. It's a Poisson distribution with which parameter?
The current iteration of governance you have, and
Yes. Okay, you're almost on it, but basically it's a Poisson distribution always with parameter 1, because in every iteration we map X entries to X random bits. Right? And basically what we're asking is like, what is the probability that a given bit was mapped only a single entry? We don't care about 0 entries, we don't care about more entries, we just care what is probability that a bit was mapped 1 entry, because that's when success occurs, right? A bit was only mapped 1 entry. Okay, so that's just Poisson 1. And we know already, we've seen this actually last week, that that's just equal to inverse of E. Okay, so this is your probability of success for a given entry in one iteration. Okay, make sense? Okay, so with respect to this, how many iterations happen until you succeed for a given entry? In expectation? Not a trick question. Yeah. E. Right? So number of iterations until you succeed. So this is basically, this becomes a geometric distribution. All right, and what is the, what is the expectation of a geometric distribution? It's actually just the inverse of the probability parameter of the distribution. So it's E. All right. So now, how do we relate that to the total bitmap size? The average number of trials until success for one entry is E. So how many trials do I have to do for n entries? Huh?
N.
Yeah, so what's the total number of bits? N times E. Correct. So that's the size of my bitmap. All right. Good. Satisfying. All right. Very clean.
What would be the expected size?
Sorry?
What would be the expected?
It's the expected size, correct.
We could in fact be worse off.
Sorry?
We could in fact be worse off than like that.
Yeah, you could be worse, but like you're probably worse by like a bounded amount with like high probability. I don't think you're going to be much worse.
That's true.
Okay. So note that this is also our construction time, because this reflects the number of times that you've tried to hash each entry. That's what we want to measure here. Okay, so now we have the size and construction time analyzed. Now let's move on to a thing that all of you were a little bit concerned about before. What is our worst case query cost? Yep. Okay, let's begin. So we want to ask, how many bitmaps are there to traverse, right? And here we care. So here what I'm asking you about is like, let's suppose like I'm really interested in like a query that has to traverse all the different bitmaps. What's the cost in that case? So basically, this is going to govern my cost. That's the number of hash functions I have to compute in the worst case for a query. That's going to be log of something, right? Why? The sizes of the bitmaps decrease by the same factor in each iteration, right? So, so the total number of iterations until my construction algorithm succeeds is just log of n with this factor by which the bitmaps are, changing size. Is that a comment? It's not quite going to be the natural log, but almost. It's something, it's going to involve E and yes, Kyle?
So the entities see in a given iteration. The one that failed moves to the next bucket, that's the 1 minus 1 over each.
Right.
So that failed, this is basically the factor in which the size of the next bucket, like in the previous bucket, let's say is n, and the next iteration is n times once bracket open, once subtract 1 over each. So
yes.
Once subtract 1 over each.
So the basis you're saying 1 minus 1 over e. So you have exactly the right intuition. The only technicality is that you actually need to take the inverse of that. So wait, is that what you said? 1.
No. No, I said the opposite.
Okay.
So yeah, you're right.
Okay. So just trust me on this. You take the inverse of that. It's something like 1.58. Plug that into the log, and that's going to be the number of bitmaps. But it comes exactly from what you said, which is that we're interested in the number of entries that don't succeed. And that's, so what we're interested in is 1 minus the probability of success, and it's kind of how we derive this factor. Okay. So this is the number of bitmaps. So this is, okay, well, we have a hash table here, but the hash table has logarithmic complexity. Hash tables are usually supposed to have constant time complexity. So this is a little bit disappointing. But we might ask, is it really that bad? So why is it not actually as bad as I'm presenting here? Okay, I see two hands. I want to see a third hand. Yes. Exactly. And why might we be better on average?
Like we just saw before, average is the hash function. But it's really for each.
Right. Correct intuition. Does somebody want to add something? Yes? No? Was that a hand?
Yeah. Oh, I think it was already answered. I was gonna say, you don't have to go all the way to the last bit matter.
Yes.
Yeah.
That's another way of saying it. Exactly. Other comments? Yeah.
The bitmap size is decreasing exponentially, so most of the bits are in the first few bitmaps.
Yep. That's exactly right as well. So now we're going to take all of these different intuitions that you've said and we're going to apply them, basically observe that, for an entry that encounters a 1, that entry can terminate immediately, right? An entry that encounters a 1 does not need to traverse the rest of the bitmaps. And then also note that it's only for very few entries that we must go all the way until the very end. Okay, so take those two things together and let's try to use that to analyze the worst case expected query cost. So now, not the worst case, but the expected worst case. And how do we do that? Well, we observe that for an entry that finds a 1 in this bitmap, right, it terminates after just one access. What's the probability that the entry ends here? It's this probability, because this is a probability of failure. So with this probability, we have to do one additional access. What's the probability that we get all the way up here? So yes. Yes. This is what you said, right? Oh, no? Okay. Okay, right? It becomes exponentially less and less likely that you visit subsequent bitmaps, right? And each access contributes 1. It's an extra hash function that you have to compute to get the total cost. So what do we do now with these? How do we use these expressions to calculate the expected cost? Parth.
Sum them up, but the coefficient is gonna be like I, so I times the,
I times?
so the probability times the value. So like, for the second one, you have to do 2 accesses. So we multiply 2 times that, and like 3 times that.
Not quite. Okay, so it turns out you can actually just add them.
Okay.
Right? And you could just add them because like each one of them is kind of like an indicator variable.
Oh, okay.
Right? So it's kind of like you multiply each one of them by 1, but because you do one access for each one of them, but it just stays that probability because you multiply by 1. Okay, and then you take the sum of this, right? And the sum of that is actually just going to be equal to this thing. We've already kind of seen this expression, but it's constant time, right? It's constant time, and it's not even such a high constant. Okay, so that's kind of nice. So now we've kind of finished our analysis. We need n times e bits. We have a strictly speaking worst case query cost of log n, but the expected worst case is actually O1. And the construction is also ON. All right. Nice. So now we might ask, we have n times e memory. Is this actually the best we can do? Okay. So what we'll now do is to give this whole lecture a little bit more foundation. Let's ask a cute theoretical question that's not going to require too much to solve, actually. And that is, what is the lower bound for minimal perfect hashing? So what's the least number of bits that I actually need to establish a bijection, a collision-free bijection? And as before, as we did for filters, we're going to analyze this assuming nothing about the implementation of our algorithm. We're only going to analyze it with respect to the specification of the algorithm. And what is the specification? We have n entries, and and the minimal perfect hash function establishes a bijection. These are the two things we know about the algorithm. Okay. So here's how we're going to frame the problem. We're going to say, let's suppose that we have a minimal perfect hash function. The minimal perfect hash function, and let's ask the question, what do we need to add? How much information do we need to add to a minimal perfect hash function such that we end up with the amount of information required to actually represent a unique permutation of the data? Does that kind of make sense? So what does a permutation store? A permutation stores the data entries and their ordering. What does a minimal perfect hash function store? Not the data, but it does have ordering. So what do we need to add? Yeah, the data. And how much is how big is the data? So let's suppose here that if we have n entries, no, let's suppose that it doesn't depend on the size of the universe. Let's suppose that it just depends on n. Suppose that you're just trying to represent n entries. How many bits do you need? So assuming that you have n different entries. So actually, okay. So I think I see where your question is coming from. I think in this context, you can say that our universe is actually n, right? Okay, anyways, we'll start with the first thing. So the thing that we need to add is the actual data. What's the size of the actual data? N log n. All right, that's the number of, and that's because I'm kind of assuming that in this context, the universe is the same as the data size, right? I only have n entries that I'm trying to map using this minimal perfect hash function, so that's my universe size. Just put that here. What about the amount of space that I need to represent the permutation? How much space is that? Yeah. Not n to the n. N to the n represents every possible assignment, including collisions. Correct. So how big is this? That is the size of that. Okay, that's the number of bits you need to represent a factorial or like a permutation, a unique permutation of n entries. We're going to simplify that using Stirling's approximation. And we're going to remove this n log n from both sides, and now we're done. Okay, so this is kind of, I see a shocked expression. So this is, okay, so this is the amount of space that we need. This is the lower bound. And this log of e base 2, I didn't have that on the slide, but in practice, it's just 1.44 bits. Right, so you can't do any better than 1.44 bits to establish a minimal perfect hash function. And we are at n times e. Okay, what's e? E is something like 2.7. So, we're not quite there, but we're pretty close. And actually, there are other papers that are more complicated that actually do better and are able to approach this. Okay, good. That just kind of allows us to know how good we are theoretically. All right, so that's all I wanted to say about minimal perfect hashing. Are there any questions about this before we continue? Yes. Yes.
Go back and let's go back one more. So you derive this size represent the data. Essentially, are you like
including an index for each. So you order the data and then assign an index. Is that how you do it?
Yeah, what it's kind of saying, the way to kind of think about it is like the minimal perfect hash function like is mapping like every key uniquely to a slot. Imagine that in that slot, you're actually going to write an ID for the key.
For the key, yes.
And the size of that ID is going to be n log n.
Yes, so yes. And then each of them have one. But my question is, if you are ordering them, can you just use that ordering index as the position? Because it seems like if you have this order things, you can just use that order as the index. And that will be like essentially all of the universe, you pick the rank of the item and then use that as the index. And it'll be bijection.
I'm not sure I totally got that, but let's talk after class, okay?
Yeah, sure.
Cool.
That's
Yeah, let's take it after class. Other questions about this? Yeah?
Software using a filter, which could do something very similar. Yeah, so how does this compare?
Okay, great question. So what do you think?
Just from the beginning, I feel like filter is faster from here. And this says like it's not logarithmic, right?
It's algorithmic worst case, but both of them are so the quotient filter that we've seen can actually still do in the worst case. No, it won't actually do that much work in the worst case. You're right, it's like the worst case for the filters that we've seen is actually a little bit tighter than here. But in expectation, it's kind of the same.
And more space, I guess.
More space for the filter because we have to store the fingerprints. That's correct. And then with the perfect hash table, no collisions can occur, which means that if we're issuing, in the context of the key value store, if we issue queries to keys that actually exist, we have a guarantee of 1 IO per query. So that's an important difference too. So it's less memory and a guarantee of no false positives. What is the downside? The downside is that if you issue queries to keys that don't exist, you will always have a collision and have to do an IO. Whereas with the filter, that wouldn't be the case. The filter would actually help you more with queries to keys that don't exist, because if you don't match your fingerprint, you know it doesn't exist. Here, you can't actually know that. Thank you for the question. Yeah?
And use how would that affect the derivation like that?
I don't know if it makes sense to change the universe size from N to U, because like you know, look, when you're analyzing a filter, it kind of makes sense to change to have it to reflect about the universe size, because there is like the set of false positives, and you can only represent that as like a fraction of kind of the universe size. But here we only ever have n entries, right? So that's why kind of conceptually our universe is the same as the number of entries.
Makes sense for middle perfect hash. I guess once we go to the dynamic side of things, and it's no longer
Correct. This is no longer hold. This will no longer hold, and you'll need like more. You'll need more memory for this. Yep.
As an extra note on like having bijection for like unbounded number of so it's like much harder.
Bijection for an unknown number of elements. Yeah, I mean, I agree. Like,
If you want to getting a bijection itself it's a different task.
yeah, exactly. And especially like, yeah, if you have to kind of handle insertions as they come, how do you maintain that efficiently? I agree. It's completely non-trivial. And maybe impossible, but I don't know. Okay, good. Yes? So it depends on what you're trying to do. I mean, like, so it can be any value that you want to associate to a key, right? But if you're in the context of a key value store, it can also be a pointer to the location of the key somewhere else. Does that make sense? So like a pointer to a location in storage where like the key value entry resides. But it's like, this is like a general purpose data structure. Whenever you want to implement like a, any kind of static dictionary. Yeah.
I
kind of going back to the point from the start here, which is like, if it's a universe of n, I mean, if our thing is bounded by n, right, then, and he said, we could just order it, the ordering something.
Yeah. Actually, that's what I mean. So you know the events, you just order them and use the index as the dimension mapping.
So you want to order them and then,
I thought of this, so I think that works if like you know exactly.
Yeah, you know
which elements are going to happen. But I think the question that this one solves best is also the constraint is you're gonna see exactly n unique elements. You don't know what those n elements are. Like they're gonna be. For that case, I think this solves, but order doesn't solve because you don't know what's coming in, right? Right. But if you know the n elements in advance, yeah, just order it and then index by like. Yeah, I was thinking about this, but does that make sense? Like, yeah.
okay, okay. So I still don't know if I completely followed that discussion, but I'm happy to take it offline with you. We need to do dynamic perfect hashing because there's also a presentation, so I'm a little bit conscious of time. So let's get to that. Unless there's another question that's urgent, but let's say no question is so urgent that it can't wait for after class. Okay, dynamic perfect hashing. Okay, so with dynamic perfect hashing, we're going to assume that we have more than n slots that we're mapping the entries into. Okay, so that means that at the end, once you've established the mapping, some slots can be free. So you have not a 100% load factor. This is going to give us some more flexibility with the mapping, but it's still too much to hope that we'll get a bijection from one hash function just by kind of trying things. There will be collisions still, so we still need a data structure to resolve these collisions. That's going to be a perfect hash function. But in this case, this will be a hash function or a data structure that we can actually modify to resolve collisions for new entries as they come. So in particular, suppose that we now have a new key G that we inserted and it happens to map to the same slot as F. We will be able to change the mapping such that the collision is resolved. Okay, that's kind of what dynamic perfect hashing does. But note that to do that, we will actually have to fetch the original key of F, right? So we must be able to store, for this thing to work, we actually have to store the keys somewhere so that in case of a collision during an insertion, we can retrieve an original, like the original key that we collided with, and then do some work to resolve the collision. Whereas with minimal perfect hashing, we can actually totally get rid of the keys. We never need them anymore. Okay, but to handle any sort of dynamicity, we must retain access to the original keys, even if they're somewhere in storage. Okay, so the first paper about perfect hashing came up in '84 by these people. And this is a very famous and influential paper. And there's been a bunch of work on dynamic perfect hash tables since. The one I'm covering is actually a paper with a pretty cool construction that we worked on while I was at this company called Plyops. And this was written up on in a VLDB paper in 21. Okay, and I'm focusing on this one. I know it pretty well, but it's also a very space efficient and cool data structure. There's a lot to learn here, and it's actually used in practice somewhere. So that's kind of cool too. So let's see how this data structure works. And by the way, at this point, anybody who was a part of this course last year is welcome to leave. So I'm looking at you three. You're also welcome to stay, but it's up to you. I will not be offended if you leave. Okay, so how does this data structure work? So what this data structure is going to do is it's going to take every entry that we're inserting and it's going to generate a hash for it. And we're going to take that hash and divide the hash into multiple components. One component will be a bucket address. This will reflect, right, all entries that go into a given bucket address, they have this same address, right? But then we're also going to generate a fingerprint, right? So the other part of the hash is going to be the fingerprint. Okay, so now let's consider two entries that happen to be in the same bucket. And what we're saying here, so far, this looks like a filter, right? These have fingerprints and there might be fingerprint collisions, but that's the thing that we're trying to avoid here. But let's assume that we actually have full access to, keys X and Y, right? So we can make these fingerprints, in theory, as long as we like, until there is some sort of difference materializing between their fingerprints, right? If the keys are different, if we have enough hash bits, eventually there will be a difference between their hashes, right? And what we are going to do is we're going to construct a trie, and the trie is going to store the index offset of the first bit that's different in their hashes. So that's a mouthful, but here, observe that these two entries have fingerprints that here are off. So I'm only representing the first 6 bits of their hashes, and the bit at offset 5, starting the count at 0, the bit at offset 5 is the first bit that's different in their hashes. So I store that at the head of the trie, right? And I say that if I'm here, so if I go to this trie, it tells me, okay, look at the 5th hashed bit of the fingerprints. If it's a 0, go here and you will find X. If it's a 1, go here and you'll find Y. Okay? So that's in some sense the least amount of information that you need to encode the difference between these hashes. Okay, I might continue. So maybe another key is added to the same bucket, key Z. And key Z has the following hash. How should I adapt the trie? Correct. I added above because this key is different from these two keys along their first bits. Right? So I add an index here. So if you look, basically what this says is if you look at the first bit of the hash, if it's a 0, you go here and you find Z. Otherwise, if it's a 1, you go here, and then you have to differentiate between X and Y along the 5th bit. Okay? And I can continue doing this, maybe add another key Q. This is similar to Z, but different along the 3rd bit. So I'm going to extend the trie here, right? And maybe I add another entry W. That's going to be right the same as these as Z and Q along the first bit, but different along the 2nd bit, right? And so I can continue and kind of extending this trie. Okay, right? And this is the least amount of information that I have to use to differentiate between all the elements in my bucket. Okay, so that's my trie, and now basically what I can do is store the payload that I'm interested in, or maybe a pointer to where the key value entry is. I could store that at given offsets that correspond to the leaf nodes of the trie, conceptually as leaves of the trie. Okay. Okay, so with this trie, the existing keys in the bucket are fully differentiated. So I've kind of done my job at making sure that collisions don't happen. But now there's a probability that there is the difficulty or challenge of how to actually encode this thing in bits, right? Because if we're actually going to represent a trie, with a bunch of pointers, and each thing, each node of this trie is allocated in a different place in memory, that whole thing is going to become kind of expensive and not very memory efficient. Okay, so we care about how to encode this trie succinctly. Okay, note also that a query to a key that doesn't exist will always collide with something, right? But we're interested in queries to keys that actually exist, and under that assumption, we guarantee no collisions. Okay. Okay. So, how to encode this trie efficiently? This is what we'll look at now. I'm going to speed up a little bit. I want to finish this in 20 minutes so that we have time for the presentation. The first thing we're going to encode is the size of the trie, so the number of entries that I've inserted into it. And I'm going to encode that in unary. And unary is appropriate here because I'll argue for this a little bit later, but take my word for it for now. We're going to size this hash table such that each bucket is small on average. And by small on average, I mean that on average there's going to be 1 entry in each one of these tries. Right? So I'm using unary codes because unary codes are great when the average value is small. Okay, so in this case, this is not a small trie, but I'm just using it for the sake of example. So I use, it's a unary with 5 bits to encode the size of this. So that's the first part. Okay. So now I have the size of the trie. Now I want to capture some information about the topology or structure of the trie. Right? I want to capture information about the fact that there's a node, internal node here, and it has some other internal node here, and right. I want the least amount of information. Let's not say the least, but a very small amount of information to actually encode this shape. Just the shape, not the actual things that I'm representing in this node, but just the shape of the trie. Does anybody have a sense of how I might do this? Yeah.
Order kind of like the position encodes where it is.
Something like that, exactly. So let's see exactly what it looks like. What we're going to do is we're going to use 2 bits to represent every internal node in the trie. Okay? And so 0, 0 will mean an internal node with no children that are also internal nodes. 1, 1 will mean a node with 2 children that are also internal nodes. Right? And then you can have a 0, 1 or 1, 0, which indicate that, either one of your right or left children is an internal node. Okay, based on and then we're going to lay this out in a depth first order of the internal nodes. Okay, so to encode this particular trie, it looks like this. Why? Because first of all, I'm looking at this. This is an internal node that has 2 children that are also internal nodes. So that's a 1, 1. Okay? Does that make sense? Now I continue in my depth first order. I go to this node. This node has one child that's a leaf node and another child that's an internal node. So the encoding for this one should be 0, 1. So that's why I have a 0, 1 here. And then I have 2 other children here, 2 other internal nodes here, this one and this one. Both of these only have children that are leaf nodes. So for both of them, it's 0, 0, 0, 0. Okay? So this encoding, I claim, is just sufficient for uniquely encoding the shape of this trie. Does that make sense? Any questions? Yeah.
Number of bits.
We're going to encode that in a second. Yeah.
Any guarantee that this is
Well, what do you think?
just insert, there's no guarantees.
There's no guarantee, but what are we encoding here? We're encoding hashes.
Right.
So on average, it's kind of balanced because because like what we're encoding are purely random hash bits, right?
Sure.
Good question. See a puzzled face. The encoding? Sure. Okay. So I'm going to use 2 bits for each internal node to encode whether that internal node, whether the left and right children are also internal nodes. Right? So the left-hand 0 is going to correspond to whether the left-hand child is also an internal node. The right bit is whether the right-hand child is an internal node. Right? And then I'm laying this thing in a depth first order.
It's not whether it what the white child is on.
Yes. Correct. Right? Each internal node definitely has 2 children, but the question is not whether it has children. We know that an internal node has 2 children. The question is whether the children are also internal nodes. Right? Okay. So this captures the shape. Good, we have the shape. Okay, okay. What can we say? Is this too much information or is this? So okay, okay. All right. Okay, so here's an insight. The last internal node in the depth first order will always have 2 children that are not internal nodes. And so this thing will always end with a 0, 0. So because it always ends with a 0, 0, we can actually just get rid of these two zeros because it's redundant. Okay, so that's our final encoding for this particular try. Okay, excellent. So now we have the structure of the try. Now we need to encode the actual contents of each one of these try nodes. Right? That's going to capture what? That captures the first the differentiating bit offset that try node represents. So, okay, so how should we encode that? Yeah, I'm going to do depth first, but what should I actually use for the encoding itself? Unary code, why? It's always going to be small. That's exactly right. So I'm going to use a unary, right? And in this case, it looks like this because I'm representing the 0, 1, 2, and 5 in a depth first order. And I'm using unary, right? Because generally, why is it usually small? It's usually small because if I'm comparing two hashes, because they're totally random, not too many bits are going to occur before the first differentiating bit on average. So the average is small. The average is 2, actually. So unary is appropriate here too. Okay. In fact, we can optimize this more. You can actually optimize this more because you can observe that the differentiating bit offset for a given try internal node is strictly greater than the offset of its parent. So you might as well just encode the difference between them. Okay, so if you do that, you can actually get rid of a few more bits. All right, we're really fighting for the bits here, right? And now we're done with the indices. Okay, so this is a perfectly valid encoding that encodes all the information of this try. Okay, kind of cool, right? All right, nice. So what now? Now we can just kind of lay out, pointers or payloads for each one of the keys. We lay them out in, kind of the same order as the leaves appear in the try. And now let's ask the question of how to answer a query. We'll answer a query as follows. Suppose we do like a get q where this is a fingerprint. So first of all, we're going to look at the number of entries in the try so we know what to expect. Then we will go to the root node and we'll look at the index, like the offset here is 0. So that tells us to look at the first bit of the hash, and it's a 0. Because it's a 0, we know that we need to go to the left, right? And then here, the index is a 1. So we know we need to look at the next bit of the hash, and that's a 1. So we know we need to go to the right, right? And then this continues. Here, it's offset 2. We know we need to look at this bit, so we know we need to go to the right again. And finally, we get to Q. And so we know that the entry that we need to access is at this offset of the payloads of the bucket. Okay, basically what this try gives us is the ordering of that particular key in like the order of the hashes of the entries in that bucket. Right? And if the payloads are ordered also based on the sorted hashes of all the keys, then like we know which offset we need to go to. Okay. All right, good. Okay. Note that all of these fields are self-delimiting. But note that this whole thing is kind of variable length. Right? So each slot in this array is going to be variable length depending on the number of entries that actually map to it. And that's going to make it a little bit problematic because usually in a hash table, we need to have fixed length slots to be able to, access things randomly. So what can we do here? Yeah. Yeah, we need some sort of way to clear space. We're not going to do it exactly. We're going to do it. Actually, we will use something similar to a quotient filter. What we're going to do is we're going to define a block, and a block is going to be a unit that contains a bunch of variable length slots, right? And a block is fixed length, but it contains a bunch of slots inside, and like that kind of gives breathing room inside the block for different slots to be variable length. So, okay, and like the whole data structure is just going to be an array of blocks, each one of which contains a bunch of slots. And each slot contains a bunch of entries. Within each one of these slots, I actually represent that trie that I showed you. Okay, so that means that when I hash a key, a bunch of the first bits are going to identify a block. And then within that block, the next couple of bits, for the next maybe however many bits, I'm going to represent the slot ID. Okay, and then the rest will be the fingerprint that I actually used to construct the trie. Okay, so that means that suppose that I'm trying to insert an entry. I'm inserting entry X. To be able to insert an entry, I have to go to the appropriate block. And then, because the slots are actually variable length, I don't know which slot to go to. I actually have to scan the entire block from the beginning. Each one of the tries that I described are self-delimiting. So if I traverse them sequentially, I know exactly where every slot begins and ends. So I know how many slots I have to skip until I get to the target slot. But the point is that I have to kind of do it using a sequential scan within the block until I get to the appropriate slot that I'm looking for. Okay? Okay, and then I might actually insert it into that slot. And that's going to have to push all the other slots in the bucket to the right because I have to clear space. I could have overflows. And if I have overflows, I can store them in something called an extension block. Okay? Good. Okay, now note that with more slots per each one of these blocks, two things occur. On one hand, I have less variability in the overall size of the block because I have, kind of an average over more elements that are of the same distribution. So with more elements, there's just kind of less variability in their total size. But on the other hand, so with more slots per bucket, I'm going to have fewer overflows. But on the other hand, that's going to cause my block size to become bigger. And so my cost of queries, my cost of kind of traversing the block is going to be higher. So there's some sort of trade-off here between the number of overflows that happen and the cost for traversing a block. Sorry that I'm speeding through things a little bit. Yes, question? The block is sized, sorry?
The block generally the size of the page is smaller than some disk.
Smaller. It doesn't correspond to the page, to size of the page on disk, right? It's the block is just like it's like a tuning thing that you use to kind of balance between these two things.
Okay, so that if it's smaller, then generally that scanning over is going to be dominated by the actual access to page on this.
Yes. So if the data that you're trying to retrieve is actually, you have to do an IO to get the actual key value pair, that's going to mask the cost of traversing the block. So it might not be that bad. Okay, let's continue. I really want to kind of finish this soon, and then we can take questions maybe offline at the end of class. Okay, so now I want to do like a bit of a space analysis. Now I explained to you the data structure. I want to analyze it. And in particular, what I want to look at is how much space does this perfect hash function take up? The perfect hash function is basically the trie, right? Okay, so what we care about is like how much space on average does each one of the components of the trie actually takes up? How many bits? So what I'm going to do is, first of all, I'm going to look at, assuming a given number of entries in a slot, how big is that particular field? And then I'll kind of show you some patterns that emerge. So just for the size of the trie, right? As I have more and more entries inside a slot, right? The encoding just increases by 1 bit for every additional entry that I have. So that's the number of bits, right? This field is very easy to analyze with respect to the number of entries in a slot. Good. What about the topology field? Let's look at that as I have more and more entries in a given trie. So if I have 0 entries, I don't have a trie. And if I have 1 entry, I also don't have anything to differentiate between, so I don't actually have a trie. If I have 2 entries, I need 1 node to represent them or to distinguish between them. But as I said, whenever I can always get rid of the last 2 bits because it's redundant information. I know that I know that the last node of the trie, right, just has 2 children that are just leaves. So I also need 0 bits. It's only from the case that I have 3 entries and onwards that every subsequent entry in the trie costs me 2 additional bits. Okay? Okay. So, right, so if I have 5 entries, I need 6 bits. Okay, so that's the topology thing. Let's look at the indices. So again, as the number of entries in the trie increases, how many bits do I need on average? So suppose I have 0 entries, there's no trie, 0 bits. Suppose there's 1 entry, there's nothing to differentiate between, 0 bits. Suppose there's 2 entries. So now the question is, on average, how big is this field? How big is it on average? For every 2 bits that I'm looking at the 2 hashes of the entries, there's a 0.5 probability that they match and a 0.5 probability that they don't match. So we might ask, after how many bits are they going to be different? In expectation, 2. Right? So in expectation, the first different bit occurs after 2. So that's kind of what I need to, that's also the average of the geometric distribution with probability 0.5. Okay, so on average, I need, assuming that I have 2 entries in the trie, I need 2 bits. If I have 3 entries, there's 1 more index field that I need to encode. Its size is also 2 bits, so I add that to the total cumulative size. Right, and for every additional entry, it's in expectation 2 more bits that I need to add. Okay, so now I know how big each one of these is in expectation with respect to the number of entries in the trie. How do I now analyze the total size? Yeah. Well, I need to take into account the probability of actually having this number of entries in a given slot, right? I don't just add them together. I need to take a weighted average, a weighted sum, in fact. How do I do that? I need you to say a word. It's a name of a distribution. It starts with P. That Poisson. Okay, so I'll add those, but I'm gonna weigh them by the Poisson. I'm gonna size the whole hash table such that on average, 1 entry is gonna map to every slot. So the lambda of the Poisson is 1. And then, right, given a probability that I end up with a given slot size, I multiply that by the expected size, for a slot of that size. And on average, that's actually 3 bits. And what's the intuition for why that whole thing is 3 bits? Because on average, every slot is pretty small. Like every slot contains 1 entry on average. If there's only 1 entry in a given slot, I don't even have a trie. So in most cases, there's no trie. The trie is just for the case that, for the odd bucket that has a lot of entries, then I can fully differentiate between them. But the common case is when this whole thing is very, very small. Yeah?
When you first create this entire data structure, it's actually less than 1, right? Because you are allocating extra capacity over to have new entries from it.
Yes, correct. So you're right. So the analysis that I'm presenting is actually great point. It's reflecting you being at capacity after you've inserted the n entries. But you're right that like up front, when you allocate this thing, it takes up a lot of space before you inserted the first entry. Okay. So, so it's 3 bits if you just consider the trie, but there's some overhead, due to extensions, and maybe you need like a pointer at the end of a block to an extension. Turns out that consumes, like without going too much into it, like 1 additional bit per entry on average. So now we can kind of compare that to minimal perfect hashing. And if you compare that to what we saw before, here, the mapping. So here I'm just comparing the amount of memory for the hash function, the data structure that resolves all the collisions. And with fingerprinting, that was E times N. With the delta hash table, it's something like 4, right? So it's not actually that much more, which is cool. But here it should also be noted, we're not going to be able to achieve like the 100% load factor that we're able to achieve here. I mean, our performance might kind of get crippled if we try to get that high. We will start having like a lot of collisions and a lot of extensions. Average query cost is about the same, and then fingerprinting does not support insertions with the delta hash table. We can support insertions. Technically in constant time, you have to traverse the block, but let's assume that the block is of constant size. So, okay, good. Construction for both of them is linear, and I finished by 2:30. Good.